Hey, what's up? Welcome to Studying with, welcome to a video where this time we're gonna talk about how we can find relationships between all the different forces we calculated. So, let's just start off with a problem, actually. So, let's say we have a thing here, and then it drops down, and we have a track, and it goes like this. Let's say we know this height is h, and let's say there's a spring here, and the spring is compressed x. Is compressed x meters, so x, yeah, it's just compressed x meters. The spring has k as its coefficient, as its spring constant, and it's a Hookean spring, so it follows Hooke's law, and yeah, and the radius, this loop is a circle. This is flat on the ground. So this loop is a circle and has radius r. Let's say I had a box here, and ignoring friction, ignoring air resistance, ignoring all like those forces that can slow us down, leach energy out of our system, I want to find how fast the box is going when it reaches the top here. Yeah, this is a kind of a big question. But all we have to do is we have to apply this thing called conservation of energy. I'm sure you have all heard of like what conservation of energy is. Like, energy in the start of the thing is going to be the energy at the end of the thing. The energies stay the same. So yeah, that's all we're going to do. Let's consider the initial energy state. So our total mechanical energy, which is just the fancy name for the total energy of the system. Right. So my initial total mechanical energy, right? What kinds of energy do I have? Well, am I moving? No, the box isn't moving, right? I just have it compressed against the spring, but I have to have some spring potential energy. And I also have some gravitational potential energy relative to the ground here. So UG. Some other things we have to know. We have to know the box has mass m, and yeah. Okay, so I can calculate that my initial energy is equal to spring potential energy, remember 1/2 kx squared, plus my gravitational potential, which is mgh. Now, I have to find what my final total mechanical energy is when I get to this point. Right? So what kind of energy do I have? Do I have spring potential? No, there's no spring here. Do I have gravitational potential? Yes, I do. Relative to the ground here, I have gravitational potential energy, so I have UG. And the box is no longer pressed against here, right? It's gone down a ramp. It's probably going to be moving, and we're going to say we're going to have a kinetic energy. So what's important to note is that kinetic energy. What's important to note is that if we started with more potential energy than we ended, all the rest of the energy is going to be kinetic energy, right? Because there's only two types of energy we've covered. We've covered potential, we've covered kinetic. So if this potential, these two have to be equal, right? Final and initial energy, conservation of energy. If this potential energy is greater than this one, then we know the remainder of the energy has to be kinetic energy. If they're equal, then they're all potential energy. And if this one is bigger, then something probably went wrong, because law of conservation of energy says we can't exactly get more energy than we started with unless we applied an external force onto the system. Right? So like if I push the box higher, like I lifted the box higher and it gained more potential energy or something like that. If we just let the system work, then all the potential energy is going to turn into, or some potential energy will turn into kinetic energy. Or 0 turns into 0. So now let's get to calculating this. This is m. See, the mass of the box is the same, mg, but this time the height is 2r. Right? And then my kinetic is 1/2 mv squared. My goal is to find v, right, the velocity of the box. So, this is going to be a bit, that was a bad idea. Okay, bad idea. What I'm going to do is I'm going to just set TME equals TME prime. Alright, so on the left side I get this stuff. So on the left side I have 1/2 kx squared plus mgh is equal to mg2r, 2r times plus or 1/2 mv squared. Now I'm just going to move this onto this side, so I get or I can move, yeah, I move this onto this side, and I'm just going to flip the sides. I'm just rearranging the equation right now. So I get 1/2 mv squared is equal to 1/2 kx squared plus mg and then h minus 2r, right? Because I subtracted mg2r from here, and then I can just like use distributive property and get like the mg up there, right? And then I just have to divide both sides by 1/2 m, and then take the square root of both sides. So yeah, let's just do that. We divide both sides by 1/2 m, we get v squared is equal to 1. The 1/2s go away, so we get kx squared over m plus 2g h minus 2r, right? So then I just know my velocity is the square root of this, which is the square root of kx squared over m plus 2g h minus 2r. Yeah, we took a really complicated problem and we just found the answer to it because we used the law of conservation of energy. And yeah, we just considered all the energy at the start of the system, all the energy that went in, and then all the energy that came out of this, or that was at the end state, so initial, end state. And yeah, we just put down the energy, we wrote down all our variables, and realized we have to solve for v, velocity. That was what we were asking in the beginning, and we see an easy way to rearrange this equation to solve for velocity. Yeah. So there you go. Law of conservation of energy right there.